Related rates, examples, objectives. By the end of this lesson, you should be able to solve more challenging related rates problems. That's all this video is all about. Just some more related rate problems. So this first one here. Water pours into a fish tank at the rate of 3 feet cubed per minute. How fast is the water level rising? H. How fast is the water level H rising at the base of the tank with the rectangular dimensions of 2 by 3? Hey Dave, let's give us a picture here. So again, let's look at the givens and the wants, right? So water pours into a fish tank at a rate of 3 feet cubed per minute. Now notice the units, feet cubed, this is volume. Also notice it's water pouring into a tank, that's going to be volume anyway, but the units kind of give it away. And notice this is a rate. So the given is dV dt equals 3 feet cubed per minute. How fast is the water level H rising? So that's our want. But again, look what it's actually asking. How fast? So that's a rate. So we want the rate of H. So the want is dH dt. That's what I don't know. That's my crappy question mark. How fast is the water level rising? It's the base of the tank is a rectangle with dimensions 2 by 3. So they give us the base of the tank. So this is a constant. That's not going to change ever. Okay, so how am I given my wants? Now let's try to relate these two, right? The whole point of related rates is to relate the two things. So I need to relate velocity with height. Volume with height in this cubic thing. Like we talked about in the last video. The volume of this guy, volume of anything, is area of the base times height. That's how I found the volume of anything that's not pointy. My base here, again, given to us, it's a constant, it's never changing. So it's a 2 by 3, 2 times 3. Height is just h. So I get my volume equals 6h. Now I gotta take a derivative of both sides with respect to t, because that's what we always do. So we're gonna take d of dt to both sides. The derivative of v is just 1, dv dt. Wrong variable. Derivative of 6h is just 6, wrong variable, dh dt. Again, look at our givens and our wants. They gave us dv dt, that's 3 feet per minute. So this guy right here is 3 feet cubed per minute. And I want this guy, 6 dh dt. Right? Divide by 6. And we get dh dt equals 1/2. Now units with it, I do want to know the units. Man, I'm not getting any better at that. I do want to know the units, right? I always do from here. dh dt, height, we were talking about feet, so this is feet. Time, we were talking about minutes, so feet over minutes. And that's your answer. Again, you can do it from here. Don't forget this is feet and feet. So 6 was 6 feet squared. So when you divide it by it, this was feet squared. And these canceled out. So you only left with 1 foot on top. Any way you want to do it. You do want to have the units there though. So that's our first one, right? The first one's kind of easy. It was supposed to be kind of like last time. Let's move on to the next one now. It's a little more challenging. A 13-foot ladder leans against a wall. I guess this is the wall. The bottom of the ladder is 5 feet from the wall at time t equals 0 and slides away from the wall at a rate of 3 feet per second. Find the velocity of the top of the ladder, at time 2. Whew. Let's get situated now. A 13-foot ladder leans against a wall. So you can tell by these triangles here, maybe it's hard to tell. This is the wall. Wall here also. Our ladder is the hypotenuse because it's leaning against the wall. It's my ladder. It is 13 feet. That is a constant. That ladder is never going to change. Same thing in this picture. I'm not going to go into this detail. I just don't like it. It's my terrible wall. They're not the same. Anyway, that's what's going on, right? Here's my wall. It's leaning against the wall at 13 feet. It's sliding down. This guy's sliding down. And that makes this guy shoot out this way. Alright, same thing happening there. It's going out that way. Let's talk about what they tell us. We still need our given and our wants. So the bottom of the ladder is 5 feet from the wall at time equals 0. So like this one looks like this is when it just starts, this is 5 feet from the wall when time equals 0. Now a couple things here. This thing's moving, so this is actually not a constant. right? This guy's moving that way. It's actually going to get bigger. You can see down here. So I can't just plug in 5 for my x. It's constantly moving. I can't plug it in until the end. So let's keep that in mind. That will get plugged in until the end because it moves. It's not a constant. Compared to the ladder here, ladder's never going to change. It's always 13. I can plug that in right away. We'll get to that in a second. And slides away from, so we have a 5-foot ladder on top, and slides away from the water rate of 3 feet per second. So this is sliding away at a rate of 3 feet per second. We got to visualize that though. So what we do is we pick a variable for this side. Let's label this side with the variable. Let's make it x. This side will also be x. Right? And they tell me that the slides away at a rate. So we have a rate here, 3 feet per second. We have a rate for x. Do you know how you make x a rate? You make it dx dt. Right? To take the derivative with respect to time. So I know dx dt is 3 feet per second. Right, so this is moving at 3 feet per second. So every second it's moving 3 more feet out that way. Find the velocity of the top of the ladder at time t equals 2. So notice it says velocity. That's just a rate. It's a fancy way of saying a rate. Because it's saying how fast. Top of the ladder at time equals 2. Well, what's the top of the ladder? Well, that's this guy right here. So what we gotta do is label this whole side also. We already have this side as x. We need to name this side. Let's make that y. So this side is also just y. So what they want is the rate of the velocity of this y thing here. So we need a rate, dy dt. And we want this when time equals 2 at 2 seconds. So I have my given and my want. I have my x and my y. Now I want to relate these two things. Look at this picture here. Is there any way I could relate these variables? X, y, and the 13. Well, here's a little hint. These are right angles because it is a building. Right, so the best way to relate these things? Pythagorean theorem. My favorite formulas in all mathematics. X squared plus y squared. Let's label this as e squared for now. Right, the Pythagorean theorem. There's one catch though. Make life easier on us. This is a constant. Like I mentioned before. That letter is never changing. That letter is always going to be 13 feet. So I don't have to leave the square there. I can actually just plug in 13. Because it's always going to be 13 no matter what. This 5, I can't plug in. That's changing. It is x. It's getting bigger. It's sliding down. Cannot change for that. Same thing with the y. Y is changing. The z here, though, that's always going to be 13 feet. So I can just plug it in. So my actual equation relating these guys is this now. That's actually very important and very helpful right now. So I got my equation. You remember what's next after we do that? We're trying to get these equations here, these dx dt. So let's take a derivative of this guy. Take a derivative of both sides with respect to t. Derivative of x is 2x dx dt. That's the wrong variable. Derivative of y is 2y dy dt. And the derivative of 13 squared, that's just a number. It's a constant. 0. So much easier when it's just, right, when you just have a number and derive that to 0. Now I gotta plug things in. And specifically I want to figure out, that's what we have here. I have dx dt is 3 feet per second, that's this guy. I'm looking for this guy. I need to figure out what x and y are. At time equals 2 is when I really want it. Well, you gotta think about this logically again. Look at my picture down here. That's 13, I know it. Could I figure out what x is? Yeah, I could. Right? At time equals 0, it's 5 feet. But it's been 2 seconds since. And it's growing 3 feet every second. So if it's, at time equals 0, it's 5 feet. At time equals 1, you use that another 3 seconds. 3 feet, sorry. At time equals 2, you add another 3 feet. So when time equals 2, this is going to be 11 feet. Right? Every second it goes an extra 3 feet. So I know that when time equals 2, which is what I want, this is going to be 11 feet. I still got to find y though. Like we don't have an equation that kind of relates all of them again. Oh yeah, we do. Pythagorean theorem again. Right? I have y squared equals x squared. Sorry. Y squared plus x squared, which is 11. Equals 13 squared. Right, I could have solved this basic algebra problem plugging in for y. So I get y squared equals 121. Plus 121 equals 169. Y squared equals, see, got a little better at that, equals 48. Square root both sides, and I get y equals square root of 48. Not the prettiest, but that's the breaks. So right here is going to be radical 48. So I'm going to write the little nicer. I'm going to get 22 times 3 plus 2 times radical 48 times dy dt equals 0. And all I gotta do is solve for dy dt. So move this over. I'm going to get 2 radical 48 dy dt equals negative 66. Divide by 2 radical 48. And I get dy dt equals negative 33 over radical 48. I'm just going to leave it like that. I do need my units though. Again, don't freak out about that. Dy, why is this the height of this guy? So what are we talking about? Feet, I think? Yeah, feet. And time was seconds. So I have y, which is feet, over time, which is seconds. So feet per second. You might be wondering why it's negative. It's because look at our graph, right? The y is going down, so it's falling, so it's a negative value compared to the x, which is going to the right, which is kind of right to the right. So that's why it's a negative, right? Because the y values are going down, negative, so it's falling 33 feet every radical 48 seconds. So that's that problem. Let's move on. Classic. Water pours into a conical tank of radius 4 feet and height of 10 feet at a rate of 10 feet per minute. Right, so here's our tank. Water's falling into, and it's 4, if you look at the top of it, it has a 4-foot radius, and the length of the tank is 10 feet. And where water's pouring into it, so we're adding water in at a rate of 10 feet cubed per minute. A, when the water level is at 5 feet, how fast is the water level rising? So they want to know when the water level is at 5 feet. So water right here is the water level. When it's at 5 feet, how fast is it rising? So let's talk about that. So they're saying when h is 5 feet, because that's my water level, how fast is water level rising? Well, h is the water level, so how fast is the rate? So I know what dh dt is. And let's go back to see what else they tell us, right? Water pours into a conical tank at a radius 4 feet and a height of 10 feet at a rate of 10 feet cubed per minute. Now, notice this, how it can use this cheat. Notice the units. Feet cubed, that's volume. So right here they're telling us dv dt is 10 feet cubed per minute. And pouring in, so positive value. Sometimes they'll try to trick you. It's pouring in, so it's positive. So I have dv dt, I have dh dt. So I want an equation that relates those two things. Well, we're doing cone, we need the volume of the cone. As I said before, the volume is always the same. It's area base times height. One difference here is that this is spiky. If pointy could kill you, so we make that 1/3. That's the rule for volume. If it's pointy like a pyramid or something, it's 1/3 area base times height. So that's our formula. We're going to relate these two things. Let's break it down a little bit more. Our base here is a radius, or sorry, is a circle. So this is actually 1/3 area of a circle, pi r squared, times the height h. Now, I don't want to take a derivative right now. Normally you would, right? Let's take a derivative. But look what I have. I have dv dt, and I want dh dt. If I take a derivative right here, what happens? Well, a couple things. First, two variables. Product rule. Already ugly, I know. You can hear the screams. Right? But also, if I take a derivative here, I'm going to get dr dt. I don't have dr dt. So it's a no-go. I cannot take a derivative of this guy because of the r right there. I got to get rid of it. How do we do that? Well, look at the picture trying to help you by using similar triangles. I got to get rid of that r. I can't take a derivative of it. I'm going to have dr dt. I don't have that here, so I can't do it. You got to use similar triangles. What does that mean? Well, look here. Let's set the proportion, right? We have r over h equals, we'll do a little differently than they do apparently, our big R compared to our little h. Alright, so I set it up. Still bad at that. Oh, come on. Stay. What happens here is this. The whole point is to get rid of that r. I can't have the r. So I'm going to solve for r here so I can sub it in. So I want to solve for r. Right, so we're going to use similar triangles to solve for r so I can get rid of it. I can plug it into there and I'll have all h's, which is what I want. So we're just going to cross multiply. I get 10r equals 4h. So again, I'm trying to solve for r. R equals 4 over 10h. Now I can plug that in for the r right there. So I'm going to have this. Volume equals 1/3 pi times 4 over 10. Let's reduce that to 2/5 h. 2/5 h squared, because that's r is squared, times h. Right? Isn't that the best thing in the world? Yeah, I know it's ugly. Get used to it. Right, so that's all it is. Right? I have this equation. I can't actually take the derivative of r because I don't have dr dt. It's gonna be a variable. It's not t, so it's gonna give me dr dt. Don't have it, so I gotta replace it. I do have dh dt, so I gotta get rid of that guy. How do you do it? Well, you have similar triangles. So you gotta set the proportions. This r over h equals r over h. Cross multiply. You want to solve for r, so you can plug it in for it. So we got r equals 4 over 10h, which is 2/5 h. It's an h. Plug it in for your r. Notice that r is squared, so all that's squared. So you have to do a little bit more math. So you get 1/3 pi, let's square both of those, 4 over 25h squared times h. We can do better than that. We can simplify that. We're going to get 4 over 75 pi h cubed equals v. Right? All that basic algebra. Simplified it. 1/3 times 4 over 25 give me 4 over 75. There's a pi there. H squared times h equals h cubed. Right? All that math. Not even done yet. Right? Because I don't have the dh dt's. So let's do that. Right? Once I have my equation actually works, let's take the derivative with respect to t to both sides. And I'm going to get 1 dv dt. Wrong variable. This is all just a coefficient to that, right? That's just like having 25h cubed, just bring 3 down. So that's not going anywhere. Bring this 3 down, subtract 1 off. I'm going to get 12. And when you bring it down, it's 3 over 1 times 4 over 75. So you want to think about it. So when you bring that 3 down, it's 3 over 1 times 4 over 75. So it's going to be 12 over 75. Pi h squared, wrong variable, dh dt. Almost done. Right, now we got to plug everything in. We took our derivative, plug everything in. What do we have? I know dv dt equals 10. The rate of the volume is that. And I know I want the height to be 5. So this is 10 equals 25 over 75 pi. I want the height to be 5 squared dh dt. Now all I have to do now is some math. This is 25. 25 and 75 reduce. I get 10 equals 12 over 3 pi dh dt. Well, 12 over 3 is 4, so I get 10 equals 4 pi dh dt. Divide by for that, and I get 10 over 4 pi equals dh dt. Don't forget the units. Again, people always overthink it. Oh, I'm so bad at that. All I do is, what is h? What is t? H happens to be feet, that's height, and the t is minutes. So feet per minute. And that's our rate. That was only A, by the way. B. Actually, let's write A here first. I'm going to do B right here. B. As time passes, what happens to the rate at which water level rises? So this is like a conceptual understanding. So we're pouring water in. Right? Notice how this end is smaller than this end? So when you pour water in, the water's going to rise really fast up. Then eventually, it's going to get so much volume to occupy, it's actually going to go smaller. It's going to start increasing at a slower rate. Right? It's really easy to fill this part up, but it's a lot harder to fill that part up. So the rate's going to decrease because there's more volume to fill. Okay, and that's that problem. Next one, more related rate problems. Let's see this one. A person is tracking a rocket 10 kilometers away in vertical flight through a telescope. If when the angle is 60 degrees, the rate of change of the angle is 0.5 rad per minute, how fast is the rocket traveling? So here's a picture again. How nice. Let's talk about what they gave us. Person tracking a rocket 10 kilometers away. So that's 10 kilometers. That's not going to change. That's probably a constant. Good for us. A vertical flight through a telescope with an angle of this, 60 degrees. So that angle is 60 degrees. The rate of change of the angle is 0.5 rad per minute. So already we're talking about the angle. That's not going to be a constant, right? As this rocket goes up, that angle is going to get higher and higher and higher. So at 60 is not a constant. 10 is, 60 is not. So this tells us the theta dt equals 0.5 rad per minute. Right? Because it's the angle. So the rate of the angle, rate of change. Remember, any times rate, you put over dt. How fast is the rocket traveling? So this is my given. How fast is the rocket traveling? So that's my want. Now let's talk about this. Y. So dy dt. Right? How fast is the rocket climbing? Dy dt. So I know they gave me the speed of the rocket, how far we are away from the rocket, the angle initially, the rate of change of the angle, and then they want to know how fast the rocket is traveling. So again, we got to relate all this. Look what we have. We have an angle, a side opposite, and a side adjacent. This is going to be a trick question. And specifically, O and A, TOA. We're going to use tan of our angle, theta, because again, it's constantly changing, equals opposite of adjacent. So let's put y over x or something like that. It's opposite of adjacent. Now, keep in mind on this right here is adjacent. It's never going to change. That's where we're standing. It's 10 feet away. This is a constant. So we actually plug it in. Our formula is actually this. Tan theta equals y over 10. This is changing. That rocket's climbing. That angle is going to get higher when the rocket climbs. So those are changing. That's my equation. Now, let's do what we always do. Take the derivative both sides with respect to t. Keep in mind on this one, let's rewrite it to make it easier. You guys have a hard time with that. It's 1/10 y. So much easier to take a derivative that way. Anyway, derivative of 10 is secant squared theta times derivative of the inside, which is 1 d theta dt. A little chain rule there. On this side, right, instead of taking a derivative of that, let's take a derivative of this guy. So much easier. 1 over 10 dy dt. So we have this. Like we always do, we plug our values in. I know what d theta t is, 0.5. Done, plug it in. I want to know what dy dt is I'm looking for, and I know theta. At that angle is 60 degrees. So let's plug everything in. Secant squared of 60 degrees times d theta dt, which is 0.5, equals 1/10 dy dt, which is what I'm looking for. Now I gotta do some trig. Secant of 60 degrees. That's opposite rad 3, adjacent is 1, hypotenuse 2. Secant's opposite of cosine, so TOA. So we're going to have the opposite of that, ha. So hypotenuse over adjacent, or just 2. Don't forget it's squared, so it's 2 squared times 0.5 equals 1 over 10 dy dt. So I just get 4 times 0.5, which is 2, equals 1 over 10 dy dt. Times both sides by 10. And I get 20 equals dy dt. Again, units, what is dy? Well, dy is 10 kilometers away, so we're talking about kilometers, so it's going up. So kilometers, and then time is minutes, so kilometers per minute. So that's how fast it's going up in the air. 20 kilometers per minute, that's pretty fast. Anyway, that's that example, right? Same idea, same concept, right? Figure out what we're talking about, have the picture help us, write an equation that relates to what we're talking about. In this case, we're doing a triangle, so it's either Pythagorean theorem or it's something we do with trig, sine, cosine, tan. So we did tan. We took a derivative of both sides with respect to t as always. Once I got that far, just plug stuff in, did some algebra, get our answer. Next one. Oh, another classic one. A 6-foot tall man walks away from a lamppost 24 feet high at a rate of 5 feet per second. So here's our 6-foot tall man that's pretty happy. Here's our lamppost that looks like a sun lamppost. Don't ask. And he's walking away. So he's going this way. Going away from that lamppost. Okay, let's talk about what's going on here then. So how fast is the end tip of the shadow moving? How fast is the shadow lengthening? So these are actually different things. We have to talk about it because it's a very distinct but important difference. And so let's kind of break everything down here. So a 6 feet tall man walks away from a lamppost at a rate of 5 feet per second. So let's talk about what that is. What is the rate that he's walking away from a lamppost? So we have like 3 different things out here. We have x, z, and y. Him walking away from the lamppost is x, right? Here's that. Distance from him to the lamppost is x. The rate at which he's walking away from it is dx dt. Now let's talk about the next thing. How fast is the end tip of his shadow moving? So they're asking about the very tip, how fast is that moving? Well, in that case, we're talking about the whole thing. We're talking about how long is the whole thing moving. I know it's weird. Why? It's just the fact when we're talking, it's kind of like the ladder. We're saying how fast is the very tip of it moving. We're talking about the whole length. So that has to do with y here. So we're talking about what's dy dt, right? Because again, it's a rate. So we're talking about the end tip. You're actually talking about the whole thing. You need the whole thing to move it. And then B, how fast is the shadow lengthening? You kind of see here, I drew in the shadow. Now you could label these differently if you want, but look how I drew in the shadow. So it's just like how we did the X here. How far away from that? Shadow is from here to here. That's the length of the shadow. So it's C. So it's going to be dz dt. So that's what each thing means, right? So how fast is he walking away from the lamppost? That's the distance from him to the lamppost. How fast is the tip moving? That's the whole base. How fast is the shadow lengthening? That's just the shadow. So from him or her to the shadow, to the end of the shadow. So let's actually solve one of these. We'll do A first. So how fast is the end tip of the shadow moving? So remember, end tip of the shadow is the whole thing. If you talk about the tip, you have the whole thing. So let's break this up into like an actual triangle. It's like this. Here's 6. Here's 24. So we're talking about the tip. We're talking about the whole bottom, which is y. And the way we're going to do these problems, we're going to separate this to 2 smaller triangles, to 2 similar triangles. So we're going to have like this small triangle here with the 6. And the big triangle here with the 24. Where this is y. Now here's the key before I start doing this one, because you might put like, oh, just put z there. We have it there. Look what's given to us. In this case, dx dt is given to us. So I need to have the x in there somehow. I have y here. So let's rewrite this in terms of x. So it's going to be z minus x. Sorry, y minus x. Sorry about that. Right, so the whole thing to get this part right here, this little part right there, we're going to write it as y minus x because I need dx in my equation. So I have it like this. Now so let's set up similar triangles. So I like to do small over big equals small over big. Cross multiply. 6y equals 24y minus x. Let's distribute that. Do what we always do, right? There's no constants here besides 6 and 24. That's why I just plugged them in the way they were. Let's take a derivative of this guy with respect to t. So I'm going to get 6 dy dt equals 24 dy dt minus 24 dx dt. And now I can plug in stuff I have, right? I want dy dt. All I need to plug in is dx dt, which I do have. It's up here. Dx dt is 5 feet per second. So this is 5. So if I plug all these in, I'm just going to get 6 dy dt equals 24 dy dt equals 24 times 5, which is 120. So minus 120. Let's move this over there and this over there. So I get 120 equals 24 dy dt minus 6 dy dt is 18 dy dt. Divide by that, I get 120 over 18 dy dt. Remember, units don't freak out. We have y, which is just one of these guys. So y is feet, we're in feet, and then t is time, is feet per second. So feet per second. Right? Y is feet, time is seconds, so feet per second. 120 over 18 feet per second. That's how fast the tip of the shadow is moving. So that's A. Now let's do B. How fast is the shadow lengthening? So again, shadow is just a shadow heavily dark right there, Z. So we got to find Z. So we're going to do it almost exactly the same. We're just going to set up the triangles a little differently. So we have this and this. This time I want Z. But just like before, I need to include X only because X is the only thing I have here. Right? I have dx dt. So I need to have that X in there. What's a little easier this time? X is this side. Let's do the same we did last time. Let me draw two bigger triangles. So we have, let's say this is 6 and this is Z. Then we have a bigger triangle. That was already kind of big. 24, and this whole side would be X plus Z. And just like we did last time, we set up the proportions. So it's going to be, I like to do small over big. 6 over 24 equals small over big. Z over X plus Z. Cross multiply. 6x plus 6z equals 24z. Once we have our equation the way we want it, we take a derivative with respect to t. So I get 6dx dt plus 6dz dt equals 24 dz dt. Honestly, probably a little bit easier if I move the 6 over first. Alright, now we plug in what we have. Dx dt from last time we learned that it's 5, it's given. And we were looking for those guys. So let's subtract that over. I'm going to get 30 equals 18 dz dt. I just subtracted 6 from both sides. Divide by 18. And I get 30 over 18 feet per second equals dz dt. So that's how fast a shadow is lengthening. Again, that's a very classic problem. The AP likes to do walking away from a lamppost problem. So there's that. Our last one more. One train travels west towards Denver at 120 miles per hour, while a second train travels north away from Denver at 90 miles per hour. See this picture here? This one's coming in, this one's going out. At time equals 0, the first train is 10 miles east. So at t equals 0, the first train is 10 miles east. So this guy. And the second train is 20 miles north. So that's 20 miles north. Calculate the rate at which the distance between the two trains is changing at time t0. So I'm going to go a little faster on this one. So calculate the rate at which the distance between the two is changing at time equals 0. So the distance between the two is this guy right there. They have L. I'm going to change that to Z. So we want to find dz dt at time equals 0. It's a little right angle. Right? And then let's see what else they tell us. The train traveling west, this train is going at 120 miles per hour. Well, that's the rate of it, right? And if this guy is x, that's dx dt equals 120 miles per hour. And then this one going north to 90 miles per hour. So this guy right here, dy dt is 90 miles per hour. Now we do what we always do. I need to come up with an equation that relates to all these, because I'm trying to find dz dt. Well, it's a right triangle, so let's do the most famous one. X squared plus y squared equals z squared. And in this case, I can't put any constants in. Everything's changing, right? This distance is changing, that train's going further. This one's coming in, and actually think about it, since this one's coming in, right, it's going from right to left, it's actually be a negative 120 miles per hour, because it's coming inside. Where this one's going out, right? It's like an XY chart. Going to right positive, going to left negative. Going up positive, going down negative. And by the way, but go back to this, z is constantly changing, right? This distance is changing. So I just have this equation, no constants. And let's do what we always do. Take a derivative with respect to time. Derivative x squared is 2x dx dt Derivative of y squared is 2y dy dt. Derivative of z is 2z dz dt. We can make life a little easier. Notice that they all have a 2, so you divide everything by 2 and you just get this. So I have that. Now I gotta fill in everything I have, right? I want dz dt. So that's the guy I want. I have dx dt is negative 120 miles per hour. I have dy dt is 90 miles per hour. I want this guy, so I gotta figure out what x, y, and z are though. But they told us, right? At time t equals 0, which is what I want, what's chain at time equals 0. The first train is 10 miles east, so this guy is 10 miles east. The second train is 20 miles north, so this guy, y, is 20 miles north. And they don't tell us what z is, but we can find it. We have a right triangle. So to find z, all I gotta do is draw a right triangle. This was 10, this was 20. Let's call that c, so it's going to be a squared plus b squared equals c squared. So 10 squared plus 20 squared equals c squared. So that's the 100 plus 400 equals c squared. So 500 equals c squared. So square root of 500. You can reduce it if you want. It would be 50 times 10, which would be 225. It would be like 50 rad 10 or something like that. Rad 5. Anyway, let's leave it at that though. Radical 500. And then dz dt. So if I rewrite it, I'm going to get negative 120 times 10 plus 1800 equals radical 500 dz dt. That's a 600 radical 500 dz dt. Divide by that, so you get 600 for radical 500 dz dt. Remember, units, don't freak out. T is time, z is this whatever unit we're talking about. We're talking about miles per hour. So, miles per hour. And that's how it's done. So again, just to recap real quick. Right? It's all about reading the question. So one train travels west of Denver at 100 miles per hour. That's this guy. Since you're coming in, it has to be negative 120 miles per hour. Well, that's your rate, right? Miles per hour is a rate, so dx dt. One travels north, so it's traveling north. Again, it's a rate, so dy dt is 90. At time 0, the first train is 10 miles east, so this guy's 10 miles out. The second train is 20 miles north, so I guess 20. Calculate the rate at which the distance between the two is changing. So we want to find what this guy changed. So dz dt is what we're looking for at time equals 0. Now I could easily change the time to like time equals 2. Then you have to do the math yourself, like, okay, wait, it's been 2 seconds, so this is 20 miles away. And then this is, so it's 40 miles away. So you set to work with, you easily change one thing to make it a little bit tougher. Right, but once you do that, you set up your equation, take a derivative of both sides, and if you have anything missing, go back and try to solve it. In this case, you use Pythagorean theorem. Plug it in, you're done. And this video is done.